Okay, so the last video for where we'll be talking about radioactivity and radioisotopes, and this is more applications. So there's three major applications of radioisotopes. There's many more beyond this, but this is what we'll talk about. So dating, ways to tell how old stuff is, applications in medicine, and applications in industry, which will be fun. So we'll start with radioisotope dating. The most known and the most commonly used of which is carbon dating. So you use carbon 14, 14C, which has a half-life of 5,730 years. It's normally made in the atmosphere from nitrogen-14, which is the normal isotope of nitrogen, the most common one. And living organisms maintain constant amounts of carbon-14 in their body when they're taking up nutrients and eliminating the waste. Dead organisms can no longer exchange nutrients with the environment, so for things that were alive, it's very good for dating remains of animals, anything made of plant material, and cultural things like linen and stuff made of plant material. So yeah, if in dead organisms the 14C decays, and there's some simple mathematics going from that decay equation that was in the last video. You can derive this, that the natural log of the ratio between the amount of the ratio of the amount of carbon 14 to carbon 12, the most common isotope of carbon, the ratio between those now divided by the ratio of those the ratio of those then divided by the ratio of those things now, so, and equals 1.21 times 10 to the minus 4 per year of times time. So rearranging that time equals that ratio, the log of that ratio divided by 1.21 times 10 to the minus 4. You can work out the amount of time since that organism died, basically. Although and we'll do an example using that equation, but there are other types of decay. One of the other most common is 14 potassium, 14 argon dating. It has a half-life of potassium 14 has a half-life of 1.3 billion years approximately, so that's better for dating things that are very, very, very old, like rocks. So you're talking about geological timescale type stuff there. But we will mention some other applications of medicine, of nuclear chemistry. So there's diagnostics in medicine. X-rays don't use radioisotopes, they generally just use X-ray tubes, which are an electrical discharge thing. But PET scans, positron emission tomography is what PET stands for, so it uses positron emission and uses that to scan your body. There's also therapy in medicine, radiotherapy for cancer, that involves the use of radioisotopes. So, and there's other applications as well, of course, but you don't need to know too much of that. Sometimes you need to know, depending on where you're studying, you need to know examples for isotopes used in each of these situations, but that's something you can find out on your own. And in industry, radioisotopes are used for energy, nuclear energy, we all know about that, and smoke alarms and thickness detectors and all other types of things, so we should say many others as well. Cobalt is used in thickness detectors, for example, because it's a gamma emitter, so emits gamma rays, and using a detector on the other side, you can, and how much they were absorbed, you can detect the thickness and maintain a constant thickness of whatever you're producing, whether it be plastic film or whatever. So, bit of an example question. You have a sample from a long time ago with a 14C to 12C ratio of 1.3 times 10 to the minus 12. Samples of living tissue today have a ratio of 1.08 times 10 to the minus 12. So how old is the sample question mark. So solving that is pretty easy. We have that equation for 4 log of the ratio of the amount in the thing from back then over the stuff now equals 1.21 times 10 to the minus 4 years to the minus 1 times time. So that log of 1.3 times 10 to the minus 12 on 1.08 times 10 to the minus 12 turns out to be 0.1854 equals that. So time equals 0.1854 times divided by 1.21 times 10 to the minus 4. So you're talking about 1,532.3 years before present. So that makes a bit of sense. You can use it today. Date, just using date stuff from when it's from, just using some simple mathematics that relates to those decay equations you learned before. So that's the end of the radioactivity stuff. We'll be moving on to more bonding, electrons, and some quantum mechanics from now.